Welcome to today's Explainer. We're setting the stage right now for an intense, highly practical masterclass. Look, if you have ever spent months agonizing over a machine learning model, optimizing it to perfection, only to realize way too late that you were fixing the entirely wrong problem, well, this session is built specifically for you. We're going to break down exactly how to confidently diagnose and fix failing ML systems, so you never waste months of your life on the wrong optimizations ever again. So, let's ground this in a classic startup scenario straight from ML pioneer Andrew Ng. Picture this. You just launched a shiny new cat picture app. Users upload their photos, and your highly tuned computer vision system finds all the cats. Simple, right? But suddenly, there's a huge problem. Your system is absolutely tanking in production. It's missing cats completely. It's tagging random dogs as cats. And the users? They are not happy. The pressure is completely on you to fix this right now. What's your very next move?
Okay, let's dive into this. Because the very second this happens, your engineering team is going to rush in with a super tempting but honestly highly dangerous menu of options. You'll hear things like, hey, let's just scrape more data, or we need more diverse data. Maybe they want to train the algorithm for another week, or, try a massive new neural network. They'll suggest throwing in some L2 regularization, or completely tearing down the whole architecture. But here's the harsh reality. If you just pick blindly from this menu without actually diagnosing the illness first, you are going to waste months of your engineer's time, for sure.
So rather than just guessing, we're going to follow a proven, highly structured framework to diagnose the exact problem. Here is the game plan for today's Explainer. We'll start with the cat app case study, move into perfecting your dev sets, go step by step through manual error analysis, learn to battle bias and variance, and finally wrap up with the never-ending ML cycle.
All right, Section 1, the cat app case study. This is where we establish the base camp for all our data.
The very first thing we have to nail down is how we're partitioning our data. This is absolutely crucial because it forms the secure foundation for testing literally any idea we have. Now, back before the massive big data boom, the golden rule was to just grab your dataset, do a random 70-30 split, and call it a day. But we really need to clarify the fundamental difference here today. Your training set is the data you run your algorithm on to actually build the model. But your dev or development and test sets, they serve a totally different purpose. That's the data you use to tune parameters, evaluate real-world performance, and direct the next changes your team is going to make.
Let's contrast these data sources using our cat app to show exactly why that old-school random 70-30 split completely falls apart today. Think about it. When you were building the app, you probably scraped thousands of website images to build a massive training set. Those are gorgeous, high-resolution, perfectly framed, studio-lit cats. But when you launch, your dev and test sets represent reality, which means blurry, low-res, poorly lit pictures taken from a moving mobile phone. If the data you train on doesn't match the messy reality your app actually encounters out in the wild, doing a random split just means you are testing your model on a complete fantasy.
Which naturally brings us to Section 2, perfecting your dev sets. How exactly do we set the right targets that guide us to actual success?
Okay, the crucial takeaway here is this golden rule. Your dev and test sets absolutely must come from the same distribution, no exceptions. If you evaluate your model on data that doesn't reflect your ultimate real-world goal, you are going to optimize for the wrong thing entirely. If your dev set is pristine website images, but your users are uploading blurry phone photos, your team is going to spend weeks perfecting a model that is guaranteed to fail the exact moment it hits a real mobile phone.
And to make sure your team hits that target fast, you have to establish exactly one single number evaluation metric. Just one. Think overall accuracy, or maybe an F1 score. See, if you use multiple metrics, like tracking precision and recall separately, your engineers are going to constantly argue over whether algorithm A is better than algorithm B. By forcing a single number metric, you cut through the noise. You allow the team to quickly compare algorithms, make an immediate decision, and drastically speed up those iteration cycles.
Moving right along to Section 3, manual error analysis steps. This right here is the absolute diagnostic core of our masterclass today.
I'll be honest, this is the tool that so many engineers try to skip. Why? Because we'd much rather write complex, clever code than sit down and manually stare at data. But here is the tangible, 3-step manual process you absolutely must insist on. Step 1. Isolate 100 misclassified examples straight from your dev set. Step 2. Manually examine them with your own eyes. Literally, look at the actual images. Step 3. Categorize the underlying causes of those errors. I promise you, taking just 2 hours of your day to manually look at 100 failures is going to save your team months of totally wasted engineering effort.
And this breakdown brilliantly illustrates exactly why it works. Just look at these numbers. After doing the manual analysis, you find out that 8% of the errors are dogs being misclassified as cats. Okay, 43% are great cats like lions or panthers at the zoo. But a massive 61% of your errors, they're just blurry images from user motion blur. If you had skipped this step, your team might have spent the next 6 months frantically collecting thousands of dog pictures to fix those false positives. But looking at the data, adding dog pictures is barely going to move the needle. You need to focus your pipeline entirely on handling blurry images. It's a total game changer.
Now, there is a slight risk here if you have a really large dev set. You got to split it into an eyeball dev set and a black box dev set. The eyeball dev set is the subset you manually examine to gain that deep intuition. But you must keep a black box dev set that you do not look at manually. If you're constantly staring at all your dev data, you'll subconsciously start writing code and designing features that only fix the exact specific images you saw. Splitting them up prevents your manual analysis from accidentally overfitting your model to the noise.
So, you might be wondering, how many images do I actually need to look at? The target number of mistakes you want to isolate in your eyeball dev set is right around 100. That's the sweet spot. It gives you a really solid, statistically significant sense of your major error sources without turning into an overwhelming, soul-crushing, all-day task. All right, Section 4, Battling Bias and Variance. Time to identify the ultimate enemies in machine learning. What's really fascinating here is how we can take incredibly dense, complex statistics and turn them into highly actionable engineering metrics. Think of it like this. Bias, or underfitting, simply means you are failing your training data. Basically, you have a high error rate on an open book test. Variance, or overfitting, is reflected by how much worse the algorithm does on the dev set compared to the training set. Meaning, you memorize the open book test perfectly, but you completely failed to generalize the knowledge to the actual final exam.
Once you know your enemy, you know exactly what weapons to pull out. If bias is your main problem, meaning your training error is just way too high, here are your specific tactics. You might want to increase the overall model size, like adding more layers or neurons. You could modify input features based on that manual error analysis we just talked about. Maybe you want to pull back and reduce regularization, or just entirely change up the architecture. But listen to this warning. Blindly throwing more training data at a bias problem will usually have absolutely zero significant effect. You're just handing a weak model more stuff it's already incapable of learning.
Now, contrast that with the tactics for variance, where your model is just completely failing to generalize. If variance is the villain here, adding more training data is actually the simplest, most powerful, and most reliable weapon you have in your arsenal. You can also introduce regularization techniques like L2, L1, or dropout. You could implement early stopping or strategically decrease the number of features. Figuring out whether you're fighting bias or variance tells your team exactly which playbook to execute, no guessing required.
And finally, we arrive at Section 5, the never-ending ML cycle. Let's wrap up this workshop by zooming out to look at the big picture of rapid iteration.
I really want to highlight this quote directly from our sources because it hits the nail on the head. ML production would be a much better place if ML experts were better software engineers. See, in traditional software engineering, code and data are strictly separated. But machine learning systems, they're a totally different beast. They are part code, part data, and part completely new artifacts generated from both. Because real-world data is constantly shifting and evolving, your ML systems require incredibly fast, continuous deployments just to survive out there.
Check out how this builds into a continuous rapid cycle. Day 1, you train and experiment. Day 2, you dive in and do your manual error analysis. By day 5, you've updated your data distributions and retrained. Day 7, you deploy and monitor. Top-tier tech companies absolutely do not run this pipeline over 6 months. They run this entire iteration loop in a matter of days, sometimes even minutes. They are constantly adapting to shifting data in the real world.
Which leaves us with a final provocative question for you to take back to your own desk right now. The next time your model inevitably fails in production, are you going to let your team spend the next 6 months blindly scraping more data and burning compute power, just hoping it magically improves? Or are you going to take just 2 hours today, isolate 100 errors, and figure out exactly what your system actually needs? The choice is entirely yours. Thanks so much for joining